Selamat datang di program studi S1 Matematika Universitas Airlangga. Program studi S1 Matematika berdiri pada tahun 1982. Berada di bawah naungan Fakultas Matematika dan Ilmu Pengetahuan Alam yang berubah nama menjadi Fakultas Sains dan Teknologi pada tahun 2008. Saat ini terdapat 4 kelompok keahlian di bawah koordinasi program studi S1 Matematika, yaitu analisis, aljabar, riset operasi dan komputasi, serta pemodelan sistem. Sehingga dalam program studi matematika tidak hanya sekedar mempelajari perhitungan rumus-rumus, akan tetapi juga hal-hal yang berhubungan dengan pemrograman. Program studi S1 Matematika memfasilitasi kegiatan non-akademik melalui organisasi yang bersifat ilmiah keprofesian sebagai wadah pemersatu, wadah aspirasi, dan komunikasi mahasiswa matematika, yaitu Himpunan Mahasiswa Matematika yang disingkat Himatika. Himatika didirikan pada 16 Oktober 1983 dan pada setiap tahunnya akan diperingati sebagai Red Day. Himatika memiliki 7 komunitas kegiatan mahasiswa yang tujuannya untuk menunjang dan memfasilitasi hobi, bakat, dan minat mahasiswanya. Untuk mendukung prestasi warganya, Himatika juga menyediakan berbagai informasi mengenai lomba, beasiswa, tutor mata kuliah, dan lain-lain yang dapat diakses melalui official account Himatika seperti Instagram dan YouTube. Tidak hanya itu, Himatika juga melakukan pengabdian masyarakat yang bertujuan dapat meningkatkan kesadaran terhadap pentingnya pendidikan. Program studi S1 Matematika telah mendapatkan akreditasi A, juga mendapatkan akreditasi ASIIN, Accreditation Agency for Degree Programs in Engineering, Informatics, Computer Science, Natural Science, and Mathematics. Program studi S1 Matematika berkomitmen untuk konsisten mencetak lulusan-lulusan yang penuh kreativitas serta kompetitif. Selamat datang di program studi S1 Matematika Universitas Airlangga. Program studi S1 Matematika berdiri pada tahun 1982. Berada di bawah naungan Fakultas Matematika dan Ilmu Pengetahuan Alam yang berubah nama menjadi Fakultas Sains dan Teknologi pada tahun 2008. Saat ini terdapat 4 kelompok keahlian di bawah koordinasi program studi S1 Matematika, yaitu analisis, aljabar, riset operasi dan komputasi, serta pemodelan sistem. Sehingga, dalam program studi matematika, tidak hanya sekedar mempelajari perhitungan rumus-rumus, akan tetapi juga hal-hal yang berhubungan dengan pemrograman. Program studi S1 Matematika memfasilitasi kegiatan non-akademik melalui organisasi yang bersifat ilmiah keprofesian sebagai wadah pemersatu, wadah aspirasi, dan komunikasi mahasiswa matematika, yaitu Himpunan Mahasiswa Matematika, yang disingkat Himatika. Himatika didirikan pada 16 Oktober 1983, dan pada setiap tahunnya akan diperingati sebagai Red Day. Himatika memiliki 7 komunitas kegiatan mahasiswa, yang tujuannya untuk menunjang dan memfasilitasi hobi, bakat, dan minat mahasiswanya.
Okay, can we start now? Okay, let's start. Okay, so Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. Welcome to the webinar of Mathematical Modeling in Real-Life Phenomena, proudly organized by the Department of Mathematics, Faculty of Science and Technology, Universitas Airlangga. And first of all, let's give thanks to the Almighty, who has given us His blessing so that we can gather here despite meeting virtually, and hopefully everyone is in good condition. I'm sorry. Okay, so before we begin, let me introduce myself. My name is Citra Rizkin from the Department of Mathematics, Faculty of Science and Technology, Universitas Airlangga. And I'm the MC of today's webinar. Okay, once again, warm welcome to everyone, distinguished speakers, Dr. Ebenezer Bonya from Akinten Apia Menka University of Skills Training and Entrepreneurial Development Ghana, and Dr. Windarto from Universitas Airlangga Indonesia, distinguished lecturers, fellow students, and all participants, welcome. Thank you for joining us today. It's such a pleasure to have you here. Okay, so there are 2 topics in this webinar. The first one is fractional modeling in real life with Dr. Bonya as the speaker, and the second one is on parameter estimation in mathematical modeling with Dr. Windarto as the speaker. Okay, so before we officially begin this webinar, I'd like to ask all participants to stay seated for Indonesia's national anthem, Indonesia Raya.
Indonesia, como é esse Índia? É isso. Yeah, I lembrei.
Kebangsaanku
you very much. And now moving on to the next session, I'd like to invite one of our lecturers, Dr. Fatmawati, to deliver the opening speech on behalf of the faculty as the Vice Dean. Okay, to Dr. Fatmawati, please.
Okay, thank you, Ms. Chitra. Are you hear my voice?
Yes.
Okay. Honorable Dr. Ebenezer Bonya from Kenten Apia Menka University of Skill Training and Entrepreneurial Development, Kumasi, Ghana, as the first speaker, and Honorable Dr. Windarto from Department of Mathematics, Faculty of Science and Technology, Universitas Airlangga, as the second speaker, and lecturer, student, and all guests. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. First of all, I would like to express my gratitude to all of the participants and distinguished guests for their contribution to the mathematics webinar, Mathematical Modeling in the Real-Life Phenomena. I hope that all of the participants here will find a lot of experience and knowledge of the fractional modeling and also parameter estimation in the mathematical modeling. As we know that the fractional calculus in recent times has attracted many researchers because of the memory effect in the prediction. Ladies and gentlemen, by this webinar, I hope our collaboration can be continued, especially in education, research, and community service, because collaboration is an essential component for us to move forward to face the global challenges of becoming a world-class university. Maybe that is all from me. Once again, thank you to all speakers and to everyone. Please enjoy today's webinar. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Warahmatullahi wabarakatuh.
Okay, thank you very much, Dr. Fatmawati. And before I pass the next session to the moderator, we're going to have a virtual participation. And with that being said, to all participants, please turn your camera on and make sure to use the virtual background that we have provided before. Okay, so one of my friends will take the pictures. Okay, let's wait a little longer.
Okay.
Okay, Bagas, you can start taking the pictures when everyone's ready.
Thank you, Chitra. Okay, let me counting down for take picture by participant in slide 1, 3, 2, 1. Cheers. Thank you. Because in slide 2, no one participant can turn on the cameras, and slide 3, no one participant can turn on the camera. section documentation is done. Thank you, Citra.
Okay, thank you, Bagas, and also thank you, everyone. And before, I'd like to make an announcement to all participants. Please make sure to stay until the end and fill the attendance form that will be later provided on this meeting chat box to obtain your e-certificate. Now, moving on to the main session, the presentations with our distinguished speakers, the session everyone has been looking forward to. I'd like to invite one of our lecturers, Ms. Tresna Shromilah, to lead today's webinar as the moderator. Okay, so everyone, please welcome Ms. Tresna Shromilah.
Okay, thank you very much, Citra,
Welcome.
as the mistress of ceremony. Well, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everybody.
Assalamualaikum
Waalaikumsalam
warahmatullahi
warahmatullahi wabarakatuh.
Okay, first of all, I'd like to welcome you all to this webinar held by Department of Mathematics, Faculty of Science and Technology, Universitas Airlangga. And as the mistress of ceremony said that today we will have two speakers that will deliver their presentation about mathematical modeling in the real-life phenomena. The first, we have Dr. Ebenezer Bonya from Akantan Apiah Menka University of Skills Training and Entrepreneurial Development, Ghana. Hello, Dr. Bonya.
Hi.
Okay, good afternoon, Doctor.
Good afternoon. Good morning, Ghana.
Is it also afternoon in Ghana, or maybe we have different time?
Morning, Ghana.
Morning. Oh, okay.
Oh,
Still
morning.
morning in Ghana. Okay, thank you very much for Dr. Bonya. And then the second speaker is Dr. Win Darton. Halo, Pak Win.
Halo, Bu Mila.
Okay, selamat siang, Pak Win. Dr. Win Darton is from Universitas Airlangga, Indonesia. Well, ladies and gentlemen, in the end of this session, we will have about 20 minutes or 10 minutes for question and answer. So if you have any question during the presentation, you can just write your question in the chat box and I will read it in the Q&A session. Or you also can deliver your question directly to the speakers by unmute your speaker and then you can deliver directly. But you have to wait until the Q&A session. Okay, now we will start with the first speaker who will deliver his presentation about fractional modeling in real life. But before that, I will read his curriculum vitae. Here I will share the curriculum vitae of Dr. Bonya. His name is Dr. Ebenezer Bonya, PhD, double Master of Science, and also Master of Education. We can see here that his age index by 13 July 2021, from Scopus is 19, and then from Web Science is 17, and from Google Scholar is 26. This is his education. He got his postdoctoral research fellow from Val University of Technology, funded Beach Park, South Africa, and got his PhD in applied mathematics from Kwame Nkrumah University of Science and Technology, Kumasi, Ghana, and also got a double Master of Science in Geometric Engineering and Industrial Mathematics from the same university, and then got his Master of Education and Bachelor of Education from University of Education, Winneba. He is now a senior lecturer in Department of Mathematics Education, University of Education, Winneba, Kumasi Campus, Ghana. And this is his area of specialization in mathematical biology, mathematical modeling, spatial analysis, fractional calculus, and also mathematics educational issues. And this is also his research interest in mathematical biology, thermal control, fractional calculus. He has so many research and publication we can see here. I'm sure that you can't wait to hear the presentation of Dr. Bonya. So for Dr. Bonya, the time is yours. Hello, Dr. Bonya. Okay. So Dr. Bonya will deliver his presentation by video, so you can watch the video, and after that you can deliver your question directly to Dr. Bonya. Okay. For operator, please play the video.
Good afternoon, Indonesia. Good morning, Ghana. Good morning, good afternoon to other colleagues, researchers who are joining us for today's presentation. As the moderator talk about the profile, I would like us to look at the fractional modeling in real life. That has been my research activity for some time now. I've done some work using fractional derivative in social dynamics, as well as epidemiology and others. If time permits, I shall also share with you what I've done so far using fractional calculus concept in modeling mathematical concepts. But the first presentation was centered on the fractional modeling in real life situation. My name is Bonya, Department of Mathematics Education, Amstead, Ghana. The Amstead is Akenton Appiah Minka University of Skills Training and Entrepreneurial Development. We are situated in Kumasi, Ghana. Now, introduction, that's the outline of my presentation. When you see introduction, we shall look at definition. We also look at application on the coronavirus, how we have applied this concept in modeling coronavirus. The introduction. I like to say that the concept of rate of change that leads to differential calculus aim at studying continuous change. So when we talk of differential calculus, all that we are talking about change. So basically the differential calculus that we usually look at it are the differential, in other words, the basic calculus that we usually consider in our studies are differential calculus and that of what integral calculus. These are the two concepts that we usually consider. The differential calculus helps mathematicians to evaluate the prompt rate of change and slope of curvature. And this is what we study at the secondary school: rate of change of something, speed, rate of change, velocity, and so on and so forth. These are rare applications in human endeavor. The integral calculus helps mathematicians to evaluate growth of quantities in the surface under between curvature. In other words, we are looking at the total surface area of a particular surface. We can evaluate the point from one end to one another, and that is quantify quantity within a space. They are saying that the more important point between these two branches is the fundamental theorem of calculus that serves as a bridge between the differential and integral. So this fundamental theorem of calculus is like a catalyst that bridges or leverages the differential calculus and the integral calculus. Now, the concept of fractional calculus was initiated by Leibniz and Newton. Today, this concept has attracted a lot of researchers in solving many real-life problems, including me. And I always say that when you talk of modern fractional calculus, you cannot mention any other person than Professor Atangana. He has permeated, worked so hard to ensure that fractional calculus thrived in this century, the latter century of this world. So extension was made by Riemann and Leverine from the pioneer work of Leibniz, whose aim was to answer the question asked by L'Hopital. L'Hopital was a student of Leibniz. So he posed a question to Leibniz, and the answer that was given by L'Hopital after answering the question, that is where we are today. That gave birth to fractional calculus. And you know, human being evolved, life evolved, everything that we live within evolved. Therefore, the answer posed at this time could not solve more or less what were being challenged. So Riemann and Leibniz took upon themselves to improve on this situation. So the initiation of the concept of fractional calculus began from this point. So at this point, a new birth had been given to a situation that happened 16th century by Leibniz and Leibniz, having that impetus to improve on this situation. Now, fractional derivative with singular kernel include the following: capital derivative, Riemann, Leibniz derivative, Catubella, polar derivative. These are very unknown derivative, but it's also one derivative which has a singular kernel. Okay. So, and others. The fractional derivative with power law singular kernel imposes an artificial singularity to mathematical model, and the memory effect cannot describe FLA. What happened is that instead of the prediction starting from the origin, if you have your graph, maybe origin here, then it will predict from any other point. So it introduces artificial prediction. And therefore, we can say that because a fractional calculus, it takes into effect memory, the present situation to predict in future. So that artificial singularity is the problem. So fractional derivative without singular kernel are two types, namely the fractional derivative with exponential kernel, which is normally known to be called Capito-Fabrizio fractional derivative, CF. Then we have fractional derivative with Luga kernel, known as the Atangana-Beleno fractional derivative. This and it should not supposed to be the fractional derivative. And here, what we're saying is that this Atangana is the man I spoke about. He is from Cameroon, who has been working in South Africa, University of Bloemfontein in Free State. It's one of the modern fractional scientists who have carried this to the highest level, and I think everywhere in the world his name is always mentioned. We thank him. So the Capito-Fabrizio operator allows to describe more efficiently the memory effect and do not impose artificial singularity as in the old Leibniz Capito derivative. Therefore, if I want to use any of this operator, I would prefer this one or the Capito or the Atangana-Beleno. Why? Because predicting artificially will not happen when you are using this operator. So this new operator has supplementary properties. It can be portray substance heterogeneities and configurations with different scale, which noticeably cannot be managed with other representation. So, as I say, we're becoming very complex every day, and therefore we need complex mathematical methodology in order to meet the demands of our needs. Atangana-Beleno generalized the exponential function and proposed Metluga law known as kernel of differentiation. So he generalized the exponential function, in other words, improve on the exponential function to come out of a new operator, which hinge on the Metluga function. And therefore, this is also more robust compared to that of the exponential. So the fractional order derivative with non-singular kernel allows to describe two different waiting time. Distribution time, which is an ideal waiting time for you get prediction, such as what happened in nuclear or magnetism and so on and so forth. So if you are doing a studies or research or modeling something in this field, it is difficult for you to use a lower derivative like levelized or Riemann derivative. It will not give you the desired results. This is what I'm trying to say. They're also saying that the crossover behavior of both operators is due to their capacity not obeying the classical index law imposed on fractional calculus. So these classical index law are more like the power law. And therefore, it is not every operator, let's say capital fractional operator, Atangana, Bernoulli operator, they are able to stretch the tail from their operator onto another operator by giving better prediction. That's what we're talking about here. So I also give the following definitions that will be applied for proofs of the existence, uniqueness, the positivity of capital. Here I'm adopting the fractional capital operator here. So this is the definition for the CF. So purpose of time, readers can read more about it. This is the definition for it, where MP represents the normality that certified the condemn or is equal to M1, which is equal to 1. So the integral operator of the fractional order corresponding to the CF fractional derivative defined as this, okay, as this expression. The Laplace, so we use Laplace transform to transform this and obtain this, where the phi star here, hk, is the Laplace transform, which is L phi x is t, comma bracket k of phi of x of t. Okay. So based on this definition, I reorganize my model in this perspective. So I have susceptible, which is susceptible with no issues. This susceptible with a comorbidity problem, susceptible comorbidity, recovered with comorbidity, and you have susceptible human being, with susceptible vector and recovery vector, and this expression is the transmission rate. The transmission rate. So this is the model that I came out with after looking at the dynamics of COVID, disease. COVID has so many intricacies that are not easy to understand. So after, as epidemiologists who have been modeling disease for a couple of times, I felt that now if you have a comorbidity issue, then your situation sometimes become a bit worried. So I incorporate that aspect also onto this model. So this shows you the comorbidity, susceptible human being infected with COVID-19, human being recovered from COVID-19, human being co-infected with comorbidity, human being recovered from comorbidity disease. So these are the meaning of this that I will try to explain. And this is what we have here in the slide that followed. So in every modeling, if it has to do with human beings, particularly or medical species, live species, we are very interested in dynamical behavior of that state or that species. So one of the parameters usually we look at, if you look at the threshold parameter that gives us idea about the spread of that phenomenon, what we call reproductive number. So we computed the reproductive number. We also look at, without the disease, what is the state? So the E super 0 here, this is what we call the disease-free equilibrium. And when the disease is inexistent, we solve the system, and the respective expression represent the equation that they related to. And this was what I just explained, a reproductive number. So computing the reproductive number, this is what we obtain. So the existence and uniqueness is one vital ingredient to study your model, whether there's existence of solution, the solution that obtained. So unique. So we use what we call a fixed point theory to come out with this solution. The fixed point theory was used. And I don't want to bother my audience with all these computations, and I just want to inform audience that this theory was what was used to, prove the existence and uniqueness of solutions. So now, having done that, I also realized lately that the COVID is a disease which is becoming difficult to manage. Sometimes you will hear that the disease has gone up in thousands, come down. Even in my country at the moment, the infection rate from government statistics is just 120. Can you imagine? We can be here 3 or 4 days, it will go 600 in 1,000. So I also decided to bring in what we call stochastic behavior. For the disease, there's some kind of turbulence, fluctuations. So we also incorporated stochastic dynamics into the model. So inputting the stochastic dynamics, then we come out with this equation with respect to the original model equation that I've shown to audience. So I've defined this stand for this. So what we see here, these are stochastic constants that we incorporated into the system. And this one, in the original work, I have also proved the existence and uniqueness of this. So this is the stochastic constant that we incorporated in the system. But I've proved the existence and uniqueness in the original paper. But I don't want to bother my audience with those jargon. So I try to come out with a numerical scheme that will help me to, examine the behavior of this. So after going through some algebraic computation, I came out with the following, numerical schemes. This is also for respective compartments, as you can see. Very interesting. So after that, the scheme were derived in the spirit of Adam Bradford scheme with the step size, this time interval 120. With these are the parameter values. But these parameter values were extracted from existing literature. Okay, and I obtained the following graphs based on the following parameter that I show you. For example, this is the susceptible class. You can realize that as the fractional order, increases, the number of human beings getting infected are reducing. For example, this one is a susceptible woman with comorbidity issue. You could see that as the fractional order also increasing, the number also increasing. That is reality is supposed to happen. Let's look at this one. This is the infected human being with comorbidity. So you see as the fractional order increasing, the number of people increase. So the infections are going up with respect to the fractional order. And let me state this to the audience. One thing from my studies for almost 2 years now, I've come to realize that one, the fractional order derivative always had a direct effect on the dynamics of the infection, how it moved in the space. Then let's look at this, what happened with respect to, so you also see, for example, the recovery co-inverted human being. You see that as the fractional order increasing, this is also increasing. So we can say that the fractional order had direct effect on the dynamics this and the rest. So we use the same parameter values, and we decided that let's, incorporate the same parameter with the stochastic constants and see what will happen. That's exactly what I did in the lab. And you could see that the graph that I'm obtaining here, look at this one carefully. Look at them, the shapes. Are they different from this? They are not. Except that you see the fluctuations. This is telling us that naturally, the COVID dynamics is not deterministic way as I show. In reality, they fluctuate. So today you can go here, The next day, it can come down, it can go up. This is giving a fair idea about fluctuations that come up with the dynamics of it. So, based on this, I conclude that I've examined the dynamics of COVID-19 coronavirus with comorbidity in a community. The steady state of the model were established and reproductive number was also determined. We have seen that. Exponential law was applied to study the dynamics of the coronavirus with comorbidity by establishing the distance. So this, as I told you in my talk, that this was established in the paper, and this is there. So it was established. I can say that stochastic approach was also, put on board or brought on board and analyzed and showed numerical results. So the numerical simulation results suggest that fractional order derivative and parameter will have serious impact on dynamics. So if you perturb the parameter, there will be new dynamics with the numerical solution. The fractional order, as they move or reduce or increases, also have a way, it also give a dynamics. So similar results were obtained for stochastic. So I'm just also saying here that the deterministic fractional graph that you observed, and that's you see that the shapes are not different, similar. The stochastic model exhibits some random effect. We saw the zigzag movement. The fractional stochastic numerical simulation results show that the random nature of the infection is not fixed as the fractional deterministic model. So that's a show. So I would suggest today that anybody who wants to embark on, modeling disease whose dynamics is not well understood, like coronavirus, I would prefer that the stochastic perspective must be incorporated in that to give us a fair idea about how the system is moving. So I want to say that the presentation has shown us new way things are happening, which is good. And that is the way research should go. We must always share what we found in our labs, in our various small way. End of the presentation, thank you. These are some of the references that I consulted in this work. Thank you for listening.
Okay, thank you very much for Dr. Punya for the presentation. Okay, I'm pretty sure that many of participants will have some questions or comments. So you can write your question in the chat box now, and but you have to wait for the Q&A session to deliver your question directly. So now we will continue to the next speaker who will deliver his presentation about on parameter estimation in mathematical modeling. Before that, I will read his curriculum vitae. This is vitae. Okay, his name is Dr. Windarto, and this is the education. He has graduated from Universitas Airlangga and then continued to Institut Teknologi Bandung for his magister and doctoral. And he also became invited speaker in some conference. This is Symposium on Biomatics in 2018 and also in 2019. And he also have books. This is its title, Optimisasi Swarm Particle menggunakan SILAB. Okay, using SILAB. And this is his publication. He has so many publication here and also become reviewer of some journal. You can see here so many article from journal that he reviewed. Okay, so now, ladies and gentlemen, please welcome Dr. Windarto.
Okay, thank you very much, Bu Mila.
Yeah.
Let me open the file. Okay. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Okay, good afternoon, everyone. My name is Windarto. I'm from Mathematics Department Faculty of Science and Technology, Universitas Airlangga. First of all, I would like thanks to the organizing committee for giving me an opportunity to share of my work. Here I will deliver a talk entitled on parameter estimation in mathematical modeling. Here is the outline of my talk. First, we briefly discuss about mathematical modeling, and then we present about parameter estimation as an optimization process. And then we show the estimation method where the analytical solution of the model is known, and then we show some application of estimation method where the exact solution is not known, and we end the talk with summary. Okay, we start with mathematical modeling. Yeah, mathematical modeling like a camera. A camera capture an object and it produces a photo or represent the actual object. And the model also capture a real problem or real phenomena, and it present the problem into an abstract form. It mean symbolic form, mathematical formulation form. And there are 4 stages in mathematical modeling. The first one is problem identification. Here, one should collect important and relevant information related to the problems. For example, if one needs want to model about infectious disease spread, then he or she should collect information about the disease. Also, and then the second stage is construction a mathematical model. In this stage, one should define appropriate state variables. What's the state variables? Should be used in the model, and then one should determine dynamics of the state variables. And after that, the third stage is determining mathematical solution of the model. Some model has exact or analytical solution, but most of the model we didn't know the exact solution of the most of model. And the last stage is interpreting the mathematical solution into real problem point of view. And when there are some relevant data from real phenomena are available, then we can use the data to validate the accuracy of the model. If the predicted result of the model very close to the data, then we may conclude that the model is very good, valid model. And most of the model contains one or more parameters. In order to perform accurate simulation, we should estimate the value of the parameters. And in the next section, I will show some aspect of parameter estimation. And basically, parameter estimation is an optimization process because we predict or we estimate the parameter values such that the predicted value are very close to the real data. And in parameter estimation, we should minimizing the error. We should minimize the difference between predicted and the observation data. So parameter estimation is a minimization problem. And hence, we can use optimization tool, including deterministic tool or probabilistic tool. And we we should determine the objective function of the problem. Yeah. For example, if we consider a dynamical mathematical model in differential equation, dxdt equal f function of t and x, and we have observed value of the state variable at time t, and if we know the parameter values, we can calculate the predicted value of the from the model. And for the optimization problem, we can choose one of the following objective function. The first one is minimize sum of square error. Here n, n in this formula is number of observational data, and we know that the sum of square error is a quadratic function, so this function is continue. From calculus we know the quadratic function is continue and also differentiable. So for the sum of square error as objective function, then we can use deterministic method. For example, Newton methods or gradient descent, or also Levenberg-Marquardt method to estimate the parameters whenever the objective function is sum of square error. Also in statistics, many scientists use determination coefficient. One want to maximize the determination coefficient. Basically, R square or determination coefficient is equivalent with the sum of square error. For R square, we want to maximize the value, but for the sum square error, we want to minimize the value. Also, sometimes researchers use mean absolute percentage error as a objective function. Note that the mean of percentage error, mean absolute percentage error, can be used whenever the data is not equal to 0, for all data. We should consider that the MAPE, the mean absolute percentage error, is continuous, but it is not differentiable. Since the MAPE used absolute value, we know from calculus that absolute value is continuous, but it is not differentiable. So the gradient-based method, for example, Newton, Levenberg-Marquardt, or step-based descent, cannot be applied to estimate the parameters when the objective function is mean absolute percentage error. And then we show you some application of estimation method. The first, we consider where the analytical solution is known. For example, we show you the population growth model. We present for population model, logistic growth model, compared, Richards, and VEP. VEP from Widarto, Eridani, and Purwati, modified logistic growth model. And the model, we have applied the model to describe the growth of roster and hen body weight, chicken body weight, and we compare the accuracy of logistic, also Richard, compares, and modified logistic growth model. This is the result of the roster weight, and this is the result of hand weight dynamics of hand weights. We found that the accuracy of logistic is poorer than the other growth models. Note that in his case, we use sum of square error. So Newton methods or stabilization or nonlinear regression can be applied to estimate the parameters. And then we show application of estimation method where the exact solution is not known. And actually, most of mathematical model, we didn't know the exact solution. And here we use a mean absolute percentage error as an objective function. Here we use we apply heuristic method, for example, genetic algorithm, particle swarm optimization method, and Firefly algorithm to estimate parameters in some mathematical model. Here we show the application of competition mathematical model to describe commercial bank and rural bank competition in Indonesia. Here we refer model from Bu Fatmawati et al. Here X is annual profit of commercial bank in Indonesia, and Y is annual profit of rural bank, small bank, yeah. And we have compared the Firefly algorithm FA and also particle swarm optimization, and we found that the result is has variance. The estimation result is are vary from one trial to another trial. Why? Since heuristic method use pseudo-random in operation of the method. So we should try the methods more than once. Here we apply the methods until 20 trial, and we find that the Firefly algorithm has lower variance, lower standard deviation, and also lower variance than the particle swarm optimization. Hence, the Firefly algorithm is more beneficial than the particle swarm optimization. But the Firefly algorithm is more time-consuming than the particle swarm optimization. So for practical application, we can apply particle swarm optimization since the method is simple, more simple than the Firefly algorithm, and yeah, it needs more efficient in time than the Firefly algorithm. And the last one, we apply parameter estimation from EXV spread among injecting drug users. We refer the model from Green-Halk and High. There are two state variables, X and Y. Here, X is proportion of contaminated needles at time t, and Y is the fraction of infected injecting drug users at time t. And the model has basic reproductive ratio like this. And we have applied the model to describe dynamics of its IV spread in East Java province, Indonesia. Yeah, we assume that HIV spread, yeah, only injecting only drug only by needle, by needle sharing, its IV can spread, and we ignore the other factor. But we didn't have the contaminated needle data. We only have a number of infected individual data, yeah. So in this case, yeah, we should estimate the initial value x naught or x0 and also y0. Why we should estimate, since the models need the initial value. So we also estimate the initial value x0 and y0, as well as the other parameters in the model, sigma, tau, rho, nu, and also mu. And here we use mean absolute percentage error as objective function. Yeah, and we apply genetic algorithm to estimate the parameters. Here is the sum result of estimated parameters. The result is has variance from one trial to another trial. So we choose the best value, and yeah, from the estimated result, we can plot, we can compare the predicted result, the solid one, and the observation data, and we find that the predicted result is very good. The model can describe the real phenomena very well. And from the model, we can predict that without appropriate treatment, the number of infected IDUs can reach more than 150,000 individual. And this is the summary. For sum of square objective value, we can use deterministic method. And for mean absolute percentage error as objective value, we can apply heuristic method, for example, genetic algorithm, particle swap optimization, and the other methods to estimate the parameters in the model. Yeah, since the exact solution for most mathematical model is unknown. And this is the end of my talk. Thank you very much for your attention. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Okay, thank you very much for Pak Windarto for the presentation. And for all the participants, now we will have discussion related to the two presentations before. So if you have any question, you can write it in the chat box, or you can raise your hand and you can unmute your speaker and deliver your question directly to the speakers. I see here we have one question in chat box. I will read it for you. This is question for Dr. Bonya. Hello, Dr. Bonya. You can hear my voice?
Yeah.
Okay. This is a question for you from Mr. Idris from SLU. Good presentation with good results, but what about the dimensions consistency, sir?
Yeah, that's also another problem. What I also realized for the past 2 years of my study in fractional application is that the dimension respect to the deterministic and that of the non-deterministic usually not same. So for the purpose of this work, I use only dimension that with respect to fractional. If you decide to use the dimension with respect to deterministic, you are likely not going to have the same solution, if you like, the same graph nature as the other side ought to be. And that is another thing I want people also to take note. Anytime you are dealing with a model which has been framed in fractional order, don't use the deterministic what do you call it? The dimensions. It will not give you same. It will not give you same. Yeah. Thank you.
Oke, Bu Mila.
Oh yeah, I still mute my speaker. Thank you very much for Dr. Bonya and for Mr. Idris. Maybe you wanna respond for the answer. Maybe you wanna give some confirmation. Any response? No? Okay, if there is no response, so we wait for another question from the participants. Oh, okay. Mr. Idris, you want to say something?
Still mute, Mr. Idris.
Yeah, it's okay. Thank you. Maybe I have a network problem.
Okay, so is it okay? Thank you very much for Mr. Idris. So we wait for another question from the participants. If you want to deliver your question directly, you can raise your hand and you can unmute your speaker so you can deliver your question directly to the speaker. Or you can also write your question in the chat box and I will read it for you. Well, while waiting, I have a question for Dr. Windarto. Maybe Pak Win, about parameter estimation. I want to ask, is there any specific characteristic of the model which suitable using certain method, or we just have to trial error to determine what is the best method for specific models?
Okay. Thank you very much, Bu Mila. Let me share the file, the presentation file. Yeah. Oh, sorry. Yeah, we should know that there are let me know. There are there is not I want to say there is no, tidak ada model yang sempurna ya. There is no
perfect model.
Perfect model ya.
Okay,
there is no perfect model, and also there is no perfect method in science. But a good news for our researcher, there is no perfect method, but there are many useful method to solve many problems, gitu ya. The deterministic method, for example, Newton method, and also Stephenson, Lavenberg, Marquardt. The methods are gradient-based method, since the method use gradient of an objective function. So if the objective function is differentiable, I repeat, if the objective function is differentiable function, so one can use Newton or Lavenberg-Marquardt or Stephenson method. But if the objective function is not differentiable function, we can apply the methods, the Newton or other gradient-based method. And in this case, we can use heuristic method, since the heuristic method didn't need gradient of the function. The heuristic method only need computation of the objective function. So as long as we can calculate the objective function, then we can use any heuristic method. But we should know that we need the data. So we need the data. So no data means no parameter estimation. So we need the data. The first one is the data, and the second one is a good model, a useful mathematical model, and the third one is parameter estimation model. It's mean optimization method to estimate the parameters. So we need three component. The data, the real data, and the useful mathematical model, and useful optimization method. So this is the point in parameter estimation. Okay, thank you, Bu Mila.
Okay, thank you very much, Pak Win. Clear enough. And now we'll move to the next question from Miss or Mr. Munkaila from KNUST. Assalamualaikum. Thank you for this wonderful opportunity. This is the question for Dr. Bonya. Is one can include diffusion component in his model? How about that, Dr. Bonya?
Please come again.
Okay.
What was the question?
Okay. Do one can include diffusion component in his model?
Diffusion.
Diffusion, yes. Diffusion
component. Well, if the model was to be partial differential equation, diffusion could be incorporated, but this is this ordinary differential equation in fractional derivative. And therefore, it may not work at this point. Thank you. Thank you.
Okay, this is another question. Continue from the previous question. Also to the second speaker. Oh no, this is for Dr. Windarto. For the second speaker. Okay, thank you very much for Dr. Bonya. This is another question for Dr. Windarto. How validity is the result obtained from parameter estimation as comparing to using actual data without estimation?
Okay. Thank you, Dr. Munkaila. For determining whether the model is good or not good to describe a real problem, we should compare the predicted result and the observational data. If the difference between predicted result and observational data is very small. So we are happy since the model is very good, since the prediction from the model are similar or are very close to the observational data. What the condition if we didn't perform estimation process? If we only use trial and error, and also guessing the parameter result, of course we can also perform the simulation, but we should compare the predicted result and the observational data. But we may predict estimation process will give the good result, the better result than without estimation process. Yeah. Okay. Thank you for the question.
Okay, thank you, Pak Win. Maybe Dr. Mukela, you have any response to the answer from both speakers? No? Okay. So now we wait another question from participants. Maybe you have questions to the speaker. You can write it in the chat box, or you also can raise your hand and deliver your question directly. Maybe any other questions?
Maybe me, Bu Mila,
Okay,
for
please.
Dr. Bonya. Hello, Dr. Bonya.
Yes, please.
Yeah. How about your simulation? What method that you have used to simulate the model, your model, actually for
Yeah.
the stochastic model? Which method?
Yeah, is recently Atangana and SIDA, as part of SIDA's postdoctoral research fellow, they came out with a numerical scheme for analyzing or simulating such models. And I adopted that scheme from a paper they published on COVID-19, South Africa and Turkey, which is still based on the Adam Basford method, but now incorporated in the scheme, the stochastic constants. That's exactly the scheme that I used with respect to MATLAB, where I coded and implemented using, as I said, same parameters for the Fabrizio Capito. I use the same parameters for the stochastic fractional aspect, except that here I have the stochastic constants incorporated. And that was why it was bringing up what you call the fluctuations or seasonal fluctuations in the model. So that's exactly the scheme I used. Yeah.
Okay.
Is it okay,
Thank
Dr.
you.
Papa, or
Okay,
maybe any
yes.
response?
Yeah.
Okay. We can see here that Bu Cici, you raise your hand. You can deliver your question now.
Thank you, Bu Mila. I asked to Dr. Bonya, but I think it's seldom we use we impose fractional derivatives in the fluid dynamics. So what do you think? Is it possible that we impose a fractional model in the fluid dynamics and then if what how we determine which the model is proper to use it, and how we determine it is a good things or not, and or others, maybe based on your experience, because you work in the fractional models a lot here.
Yeah, I think it is very good or laudable idea to impose fractional dynamics in fluid studies or fluid dynamics, in the sense that in all of the fractional thing we're talking about, the quantum of parameters, in other words, the parameter values that is required to simulate the deterministic fluid dynamics is always in higher values than that of the fractional. For example, if you happen to be doing this in a rare life or rare time laboratory, the cost involved that one has to incur and the machines you have to buy to obtain these parameters, if you are simulating in the fractional perspective, the quantum of parameters in terms of value is always smaller, which is going to give the same or even better results. That is one thing you must take note. In addition to that, in my presentation, I also mentioned that the Atangana-Beleno operator, which is hinged on with Luga function, it is so robust that it is able to stretch from one tail, means one operator to one another, giving you the clear, almost safe prediction. In other words, prediction without no artificial inclusion. So for me, almost every modeling, irrespective of the specialty one is doing, I always recommend fractional is the way. Even space sciences are now moving into fractional. Space sciences, I've seen Professor Beleno, who is a member of a space agency. And recently, some people I read, they are all converting their deterministic model into fractional. And I can say again that the fluid dynamics, which is PDEs, there are schemes there. There are fractional schemes for PDEs. So I recommend you could do a paper where you could have a numerical scheme for the deterministic. Then that same model, you have numerical scheme for fractional, maybe Atangana or CF. And I can assure you that if you incorporate that same deterministic parameters into the fractional, you will not get the same results. Why? Because the fractional will demand lesser parameters value than that of. So in terms of cost, it is cheaper. In terms of accuracy, because if it's non-local, non-singular, it means therefore that the prediction that we're going to predict, there's no artificiality. We're going to predict from the origin, because the concept of fractional, it is the past history, the present history put together to predict what happened in future. Thank you.
Okay, thank you very much, Dr. Bonya. Maybe any response from Bu Cici? Okay, okay. And now we have two questions here from Mr. Sharif Abdullah. I think this is two questions for two speakers. So I will read the first question for Dr. Bonya. This is from Mr. Sharif Abdullah from Untirta, Banten, and his topic focus is on stochastic process, specifically the development of the compound Poisson process model. And this is the question about the size of the significance. Is there a specific measure in measuring significance? Because he thinks that in certain fields, such as the humanities, the size of the significance will be different from that of health. What do you think, Dr. Bonya?
Well, I cannot say much about this point he's talking about, because what has been experimented from the paper that was released just last year, you're talking about the significance could be different from maybe epidemic significance may be different from other fields. It could be true, because the dynamics the relevancy of every discipline differ from one to one another. If somebody's work does not require maybe stochastic perspective, what is the significance even putting the stochastic in it? You're talking about a situation where the disease evolved. Today, one gets the national incident or the national disease with respect to COVID, you say, oh, we have 20. The next 3 hours, it has jumped to 30. The next hour again, the government says it's 200, 300. So there's a fluctuation. Therefore, as a modeler, it is my concern to incorporate what I observe, quantify in a mathematical perspective into the model so that whatever I model can situate the reality. So I agree with him. It could be not significant in other respects. However, for epidemiology, as far as I'm concerned, it is highly significant. Thank you.
Okay, thank you. Is there any response to the first answer? No? Okay, we continue to the second question. Maybe Pak Win, you can answer this question. He used test error on his model, and test error parameter estimation that he used is MSE, mean squared error, on the expected value and variance. The results of his research resulted in a simulation of going to the expected value and the variance and MSE going to 0. In your opinion, is it enough with MSE or should he use another error test?
Okay, thank you very much, Bu Mila, from Pak Syarif or Dr. Syarif. Pak Syarif, let me know, do you compare the predicted result and the observational data in your case?
No, just simulation of my model.
What do you compare in to obtain the MSE, mean square of error? What's the definition of error in your case?
Can I talk with Indonesian?
Yeah.
Yes, sir.
Okay. Ini model saya itu pengembangan ya, Pak. Pengembangan dari apa ini namanya itu Poisson model yang apa ini namanya majemuk. Cuman majemuk ini itu biasanya dia akan pakai apa ini namanya homogen si kepala sigmanya itu. Nah, kemudian saya mengembangkannya itu pakai non homogen. Jadi lebih kompleks. Sehingga di sini saya membangkitkan data. Satu membangkitkan data, kemudian saya melakukan simulasi, kemudian saya apa namanya itu compare antara pembangkitan data saya kemudian dengan parameter. Ada formulanya sih Pak sebenarnya.
Oke. I see.
Ada formulanya sehingga.
Oke, I see. Okay. How many parameters in the classic Poisson model, Pak Syarif?
Sebenarnya campuran Pak, ada banyak. Kalau misalkan dalam apa ini namanya itu, dalam model saya itu si kepalanya itu kan biasanya cuma n, tapi n-nya ini saya buat dia itu sebagai fungsi terhadap waktu. Jadinya kan YT sama dengan sigma dari apa ini namanya sigma dari xi dengan kepalanya itu kan n kan. Nah, n-nya ini saya buat dia itu sebagai fungsi terhadap waktu. Sehingga dia itu si kepalanya dia itu kadang linear, kadang dia linear, kadang dia berpangkat, kadang dia mempunyai periodik seperti kejadian apa namanya? Kejadian kecelakaan yang selalu berulang-ulang atau kejadian musiman yang selalu berulang-ulang atau apa ini namanya? Gempa dan lain sebagainya. Sehingga di situ saya buat dia itu periodiknya ada juga periodiknya dia itu mempunyai trennya dia tren linear atau tren yang mempunyai pangkat kurang dari 1, antara 0 sama 1, bisa juga lebih dari 1, seperti itu. Gitu. Jadi parameternya itu ada banyak, ada lebih dari 3 ya dalam satu model gitu. Gitu sih Pak.
Okay. So you have Poisson model and there are some parameters in the model.
Yes.
Yeah, from your description, I conclude that you test the method, whether the method can predict the parameters or not, and you use artificial data, yeah.
Yes.
Artificial data, yeah.
Yeah.
I mean simulated data.
Yes.
Yeah, yeah. Of course, you can use mean square error, but let me show the files, the slide. Yeah. Okay. Yeah. You can use mean square error or mean absolute percentage error, but we should know that mean square error take more attention on the high value of data. I repeat, the mean square error take the high value of the data. So if you use mean square error, in some cases, the difference between the predicted result and the observational data for low value of data may be very, very high. Since mean square error give attention or high value of data. Since the higher data, the higher square of error. But for mean absolute percentage error, if we use mean absolute percentage error like this, we give attention on all value of the data, for low value and also for high value. So if the mean absolute percentage error is very low, it imply very low of some square error. Yeah, and yeah, you can compare the objective function. You can try to use mean absolute percentage error to test validity of your method or your model. Okay, thank you very much.
Yeah. Thank you very much about the answer.
We wait for another question from participants. This is info for the participants. Don't forget to fill the attendance form that had been sent by the committee in chat box, because it's related to your certificate. So please fill the attendance form. Well, if there is no other questions from participants, maybe I want to ask to the speakers, maybe you can give some closing statement before we end this session, maybe from Dr. Bonya, the first.
Thank you very much for this opportunity. I would like to say that research is the engine of growth in every society. And I believe that COVID-19 has taught us a lot of lessons And when it came up early, epidemiologists, mathematical biologists, and any other people related to getting us to understand the actual dynamics of this disease has worked so hard, and that is where we are today. Where now, today, there's a vaccine. This vaccine has come up as a result of research. And I strongly believe that fractional calculus in terms of modeling is the way to go in this country. And I will encourage young researchers, then experienced researchers who have passion to relate what they study, what they do, what they work with in the realm of fractional calculus to endeavor to do so, and it will never be regretted. I also like to say that I also thank to Professor Fantuanti of your university, who is my supervisor, done very well to make sure this today program comes off as a faculty adjunct professor. And on behalf also the University of Skills Development and Entrepreneur, and also on behalf of Akintia Minka University of Skills Training, Entrepreneurial Development, and my colleagues, faculty members, and students that I teach in the Kwame Nkrumah University of Science and Technology who were able to join, and other people who joined elsewhere. I thank you for making time to listen to my talk. Allah bless you. God bless you. Thank you.
Okay, thank you very much for Dr. Bonya. And the second change for Pak Win. You can deliver your closing statement.
Okay, thank you very much, Bu Mila. Yeah, mathematical modeling is very interesting field. Since by mathematical modeling we can contribute to solve many real problems, but for obtain the optimal result, we should construct good collaboration with other fields. Referring the result from addition in base 2. In base 2 we have 1 plus 1 is equal 10. But by perform good collaboration between mathematician and other field, we can get more and more result, like 1 and 1 plus 1 equal 10. Thank you very much, Bu Mila.
Okay, thank you, Pak Win. And I demand once again for the participants, please fill the attendance form. You can see the link in chat box because this is related to your certificate. Well, thank you very much for all the presenters today. Okay. Since time is up, so we will end this session. And once again, I'd like to thank all the presenters for the interesting and stimulating presentation. Wish that we can have another collaboration later in the future. And for the participants, thank you very much for participating in this session. I hope you enjoy the program, and please forgive me for all my mistakes during this session. See you again in the next program. Goodbye. Assalamualaikum warahmatullahi wabarakatuh. I give back to the Mr. Thank you very much, Pak Win and Dr. Bonya.
Okay, thank you very much, Bu Mila.
Okay, thank you, Mr. Smila, for leading the discussion and presentation session. Okay, so everyone, we finally reached the end of this webinar. And as mentioned as Mr. Smila before, don't forget to fill the attendance form. And the certificate will be sent by email after the webinar ends. So make sure to check your inbox or spam by then. Okay, now as the final words, I'd like to thank everyone who has participated in this webinar and also to Dr. Bonya and Dr. Windarto. Thank you very much for sharing your knowledge and research experience. It was such interesting and insightful lecture. I hope everyone enjoyed it. And on behalf of the committee, I'd like to apologize if there's any mistake or inconvenience during this webinar. And once again, thank you very much for joining us. Wishing everyone a pleasant day. See you and make sure to stay safe and healthy. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, everyone.